Okay, so section 15.6, geometric series. Okay, so um, as an example, suppose I have, let's say the following geometric sequence. Then, let's say 2, 5, 2, 6, 18, 54, etc. Okay. Then we can form a geometric series by just adding up each of these terms in a geometric sequence. And so a geometric series is just a series. Well, let's recall that your geometric sequence has a general term of the form a1r to the n minus 1. And so a geometric sequence, a geometric series, is a series of the form I'll say to n of a1r to the n minus 1. So that is a geometric series. Okay. It's just some member of the partial sum sequence. Okay, so suppose that I want to find a formula to determine the sum of some sort of geometric sequence. So I guess for some notational purposes, let S of n equal the sum, let's say k equaling 0 to n of a1 r to the k minus 1. So it's the sum of a geometric sequence. Then, note the following. Let me just write down S of n by, so this is just a1 plus a1r plus a1r squared plus a1r to the n minus 1 plus a1r to the n. Okay, and now let's multiply by negative r times this above series. So I'll get a negative a1r multiplying this by negative r minus a1r squared, multiplying this minus, well, a sub 1 r to the n minus 1 minus a sub 1 r to the n minus, multiplying this by r minus a1 r to the n plus 1, so that we can determine a formula. What are we solving for? We're going to determine a formula for the sum, S sub n. And so I have 1 S sub n minus r S sub n is equal to, well, notice here that the a1r, a1r squared, a1 r to the n minus 1, a1 r to the n's all cancel. So you actually just have the first and last terms. Oh, this was n minus 1. Shoot. So that's r to the n. Notice I should have, the last term in here when I put in n was n minus 1. Okay, so sorry about that. So now let's factor out Sn. Let's factor out A1. Now let's assume that R is not equal to 1. Usually we assume that R is not equal to 1 because it'd be a very boring geometric series. It would just be, you know, A1 plus A1 plus A1 plus A1. It wouldn't, the sequence wouldn't change. It'd just be, 5, 5, 5, 5, 5 forever or whatever, 12, 12, 12, 12 forever. It wouldn't change. So that's a very uninteresting geometric sequence. So let's just assume that in our sequence that in our series R is not equal to 1. That's what I'm doing. I'm telling you to derive it. So now let's divide both sides of my equation by 1 minus R. And so I have that S sub n is equal to A1 times 1 minus R to the n over 1 minus R. And so I've derived a formula for the sum. Okay. And so that's a derivation. So let me have you guys. So now I guess I will ask you guys to turn in for Monday. Turn in the following for Monday. Okay. So prove use mathematical induction no proof derivation is just showing that something works. Proof is using some sort of logical steps to show that something works. So I've derived this, but now use mathematical induction. So I'm telling you what to use. Use mathematical induction to prove, and I guess I'll have two parts to this, to prove that the sum, because we did this yesterday also, that the sum of, well, let's say k equaling 1 to n of, let's do this for a arithmetic series, that this is equal to n over 2 times 2a1 plus k minus 1d. Okay, that's the first part. And then for the second part, so this is, I guess, problem number 1. Number 2, use mathematical induction to prove that the above formula, the sum, let's say k equaling 1 to n of a1r to the n minus 1 is equal to a1, 1 minus r to the n over 1 minus r. Okay, of course, I'm assuming r is not equal to 1. Okay, so turn these in on Monday. Put your name on the upper right corner and turn these in. Okay, so this is the formula to find the sum of a geometric series. Okay, let's do some examples. On page, more than one page, 673. Let's do problem number 1. 1 plus 3 plus 5 plus 7 plus 9. In exercises 1 through 6, determine whether the series is geometric or not. Well, notice that this is a arithmetic sequence, 1, 3, 5, 7, 9, because I'm always adding a common difference. Therefore, this is not a geometric series. So no, it is actually arithmetic. So it's arithmetic series. It is not geometric. It is, in this case, arithmetic. Let me do problem number 3. 1, 2, 4, 8, 16. Let's see if this is geometric. You mean no? There's nothing about intervals. So if we have a common difference, if you always add the same amount, then it is an arithmetic sequence. Since we're adding terms of an arithmetic sequence, this is an arithmetic series, not a geometric series. Okay, let's look at 1 plus 2 plus 4 plus 8 plus 16. Notice that the terms of the arithmetic series is just in this series is a geometric series because I keep multiplying each term in this series by 2. And so 1 times 2 is 2 times 2 is 4 times 2 is 8 times 2 is 16. And so the sequence here is a geometric sequence. Since I'm adding up the terms in a geometric sequence, this is a geometric series. Problem number 5. Actually, let's do problem number 2. Problem number 2. 1, 4, 9, 16, 25. No. A sequence is this, are these numbers, 1, 2, 4, 8, 16. That's a sequence, okay? And each of these are members of a sequence. It's some rule. A series is the sum of a sequence of terms. It is a special type of sequence. We looked at those partial sums yesterday. It's a sequence of partial sums. The members of a sequence of partial sums is called a series. the sum of members of a sequence is a series. Okay. So, 1 plus 4 plus 9 plus 16 plus 25, is that a geometric series? Well, no, because you're not always multiplying by the same amount. And so notice, to go from 1 to 4, I multiply by 4, but to get to 9, I'm not multiplying by anything. So no, this is not a geometric series. But notice that this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So this is actually the sum of a whole bunch of squares. This is actually called a Riemann zeta function. Zeta function. Okay, so if you are adding a common difference, then it is an arithmetic sequence. If you are multiplying by a common ratio, it is a geometric sequence. If you add the terms, then it's called a series. In this case, we're actually raising each of these to a power. If you raise everything to a power, it's called a Riemann zeta function. Okay. And actually, if you prove that the zeros of this Riemann zeta function in the complex plane always lie on the line where the real part is a negative 1/2, the Clay Institute will give you $1 million. It's not an easy problem, but they'll give you money. Problem number 5. 1/5 plus negative 1/5. Yes, go to the Clay Institute. That's one of their millennial problems. Okay. 1/5 minus plus negative 1/5 plus 1/5 plus negative 1/5, etc. Okay, so is this a geometric series? So the answer is yes, because this is a geometric series. Because to go from 1/5 to negative 1/5, multiply by negative 1, again multiply by negative 1, positive 1/5, multiply by negative 1, negative 1/5. And so to get to each subsequent term, you'll always multiply by a common ratio. Therefore, 1/5, negative 1/5, 1/5, negative 1/5 form a geometric sequence. Therefore, their sum is a geometric series. Okay. Let me do problem number 7. So if you look for, well, I mean, each section of this chapter give you the definitions, and also in my lecture notes, I give you the definitions at the beginning of every section. Okay, let me do problem number 7. 1 plus 1/3 plus 1/9 plus 1/27 plus etc. In exercises 7 through 9, Determine the sum of the first 15 terms of the geometric series. So let's find that sum. Yes, this is section 15.6. Okay, so I know the formula for the sum is given by the above formula. And so let's figure out what the sum is. And so I want to find the sum of the first 15 terms. The very first term is 1. The common ratio, I keep multiplying by 1/3. And so the common ratio is 1/3. And the n is 15. And so all divided by 1 minus r, which is 1/3. Okay, let me multiply. Yeah, so, right. So if, oh, no, if it's a sequence, no, if it's a sequence, then you use that other formula, the an equal a1 r to the n minus 1. That's if it's a sequence. If I'm adding up all those terms in a sequence, then you use this formula. And it doesn't really matter if it's a fraction or not, even though for fraction, I usually use it in this form, where the 1 is first. Let me multiply both sides of my equation by 3 to the 15. Both the numerator and denominator by 3 to the 15. So this is equal to, well, 1 is just 1 times 3 to the 15 is 3 to the 15. The 3 to the 15s cancel. And so I get 3 to the 15 minus, well, 3 to the 14. Since 3 to the 15 divided by 3 is 3 to the 14, well, 3 to the power 15, big. It's 1, 4, 3, 4, 8, 9, 07. Eight, 9, 07 minus, sorry, 4, 7, 8, 2, 9, 6, 9, 3 to the 14. And so S to the 15 is equal to 1, 4, 3, 4, 8, 9, 06 divided by 9, 5, 6, 5, 9, 3, 8. Okay. I can at least divide each of these by 2. 47, 82, 969. Let's divide that by 2. Seven, 1, 4, 7, 1, 7, sorry, 7, 1, 7, 4, 4, 5, 3. Okay, let's, I'm just, what I'm doing is just calculating numbers. And so, you know, there's 3 to the 15, I subtracted 1. I do 3 to the 14, subtract 3 to the 15. And now I have a fraction, so I'm trying to reduce the fraction. Okay, so that's all I'm doing at this moment. And so this is your answer. This is approximately, so the sum of the first 15 terms is approximately 1, approximately, okay, 1.4, 1, 2, 3, 4, 5, 8, 9, 5. So it's approximately 1.5. Okay, 1 second. So you use this formula for geometric series whenever you want to find the sum of a geometric series. Okay? So that's all I'm doing, is just calculating the sum using the above formula. In this section, well, so far we only have really one formula for finding the sum of a geometric series. That's right, because I'm adding up a whole bunch of fractions. Mm-hmm. So I'm doing 1 plus a third plus a ninth, etc. And so even though I'm adding up 15 terms, they're small numbers, and they're even getting smaller as I add up. Let me do problem number 9. Three plus 6 plus 12 plus 24. Let's add up the first 15 terms of that. Okay, so let us find the sum of the first 15 terms of this sequence. Right? So you're just adding up 3 plus 6 plus 12 plus 24 plus etc. Okay, so I have a formula to find the sum. The formula is just a1 r to the n minus 1 over r minus 1. And let's plug that in. So I want to find the sum of the first 15 terms. The first term is 3. Notice that the common ratio is 2 because I keep multiplying by 2 to get to the next term. 3 times 2, 6 times 2, 12 times 2, 24, etc. And so let's simplify this. Well, 2 to the power 15, it's 32,768. 2 minus 1 is 1. And so this is equal to 3 times 32,767. And so sorry, I get 98,301. So if you add up the first 15 terms of this sequence, you get 98,301. Two is 2 to the 15. Oh, so 2 to the power 15 is 32,768. 2 times 2 is 4, times 2 is 8, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. Just keep multiplying keep multiplying 2. Okay? My voice is doubled. Okay, I don't know what that means. Um, oh, someone, that means someone accidentally has on their mic. Uh, sorry, someone has on their, accidentally has on their mic on their computer. So it's echoing on your part. Sorry about that. Uh, oh, you logged in twice. Uh, you know, yes, you logged in twice, so so you're actually hearing it twice. That's why. It's because it's coming from two separate inputs. Okay. Let me do problem number 11. Yeah, yeah. If you good, now it should be okay. Okay, so let me do problem number 11. Okay, so um, 2 plus 1/2 plus 1/8 plus 1 over 32 plus etc. In exercises 10 through 15, find an expression for the sum of n terms of the geometric series. And so I want to find a formula that only involves n for the sum of the first n terms of this geometric series. So I know that S of n is equal to, well, I don't know how many formulas there are. Uh, they can all be derived from two formulas, but if you recall, on your exam, I have a page of formulas. I give you all the formulas. There's a formula sheet. And so the sum of the first n terms is a1 times 1 minus r to the n over 1 minus r. So once I know a1 and r, I can find a formula just in terms of n. So let's do this. And so the sum of the first n terms is, well, the first term is 2. The common ratio, well, to get from 2 to 1/2, I multiply by 1/4 times 1, so 1/2 times 1/4 is 1/8. 1/8 times 1/4 is 1/32. So the common ratio is 1/4. Okay, so common ratio. Well, 2 times what is 1/2? 1/2 times what is 1/8? 2 times what is 8? 4. 2 times 4 is 8. Okay? And so I get, let me multiply. Actually, maybe I'll just leave it like this. So this is equal to 1 minus 1/4. So let's do that. Let me write 1 as 4 over 4, getting a common denominator. And so I have 4 over 4 minus 1 over 4. Well, that's just 3 over 4. Now, dividing is the same as multiplying, by the reciprocal. Oh. And so let us write, this is saying dividing by 3/4. But again, dividing by 3/4 is the same as multiplying by the reciprocal, 4/3. Okay, and so 2 times 4/3 is 8/3. And so 8/3 times 1 minus 1/4n. And that is your formula. So you can find the sum of the first n terms, and notice this formula only involves n. And so once you know what n is, say you want to find the sum of the first 20 terms here of this series, I can just plug in n equaling 20 into this formula and find what the sum is. N is the number of terms in your series. And so if I want to determine the sum of the first n terms of my series, I can use this formula. And I'll get whatever answer I want. Okay, so let me do problem number 12. That's alternating like that. Let's do problem number 12. 3 minus 6 plus 12 minus 24. Let's find the sum of the first n terms. It can be in any whole number, any integer. So it's the total number of terms that you add. So n can be any natural number. N can be, 25, 17. And so I want to find the sum of the first n terms. Well, I know that Sn is equal to a1 r to the n minus 1 over r minus 1. So that's the sum of the first n terms. So let's figure out what this is equal to. So S sub n is equal to a1. Well, the first term is 3 times, well, 3 times negative 2 is negative 6. Times negative 2 is 12. Times negative 2 is negative 24. So r in this case is negative 2. Okay, so let's simplify this. Well, negative 2 minus 1 is negative 3. So dividing by 3 divided by negative 3 is a negative 1. And so let me change all the signs. So I get S sub n is equal to 1 minus a negative 2 to the n. What is the common ratio? The common ratio is what you multiply to get to the next term of a geometric sequence. And so 3 times negative 2 is negative 6. Negative 6 times negative 2 is 12. You can find the common ratio, remember, by just dividing consecutive terms. 12 divided by negative 6 is negative 2. Yes. Okay. And so you can find the sum here of the first n terms by just using this nice formula. So notice that this is actually a very nice compact formula. So if you want to find the, let's say the sum of the first 10 terms of this, right? And so if you did the sum of the first 10 terms, you get what, a negative 1023. Just plug in 10 to this. Yes, as long as it is a geometric. The same way you subtracted for arithmetic to always get the common difference. hmm Okay, let me do problem number 13. 2 plus -6 plus 18 plus -54, etc. Oh, why is R? It doesn't really matter. The only reason I usually it, notice that obviously 1 minus 7 over 1 minus 12 is the same as 7 minus 1 over 12 minus 1, right? Because you would get what, a -6 over -11, or you get a 6 over 11. Obviously, the negatives cancel, right? So it doesn't matter which way you write these. I usually write, and it's just the way I write it doesn't really matter. I usually write R second if R is a fraction, and I usually write the R first if the R is greater than 1. But it really doesn't matter. It's just my habit of writing it. No. Uh, X minus 6 is not this. X minus 6 is the same as -6 minus X, right? But if you had two negatives, canceling two negatives, is going to get rid of it. Because I changed the sign twice, and I'm dividing, so then it doesn't make a difference if you do two uh, negations. Okay, so I have a sub n, that the sum of the first n terms, s sub n, is equal to a1 r to the n minus 1 or r minus over r minus 1. So the first term is 2. The common ratio it's the same as all the previous questions we had. Uh, in exercises 10 through 15, find the expression for the sum of n terms of the geometric series. So for the last like 3 problems that we've done, the same question. Okay, so the common ratio is -3. 2 times -3 is -6, times -3 is 18, times -3 is -54. -3 minus 1 is -4. 2 divided by -4 is a -1/2. And let me multiply the negative inside the parentheses. So S sub n is equal to 1 minus a -3 to the n all over 2. And that is your formula. So that's, again, a nice compact formula. If you want to find, and that's kind of nice. So notice that you always come out with a integer answer. So even though it looks like you're going to have a fraction, it's actually not a fraction, because you'll always get a even number in the numerator, and so when they'll cancel out the 2's. What lost the step at the end? I'm not sure what? Yes, that is correct. So in the question, it says to find a formula for the sum of the first n terms. And so what I found is a formula for the sum of the first n terms in terms of n, the number of terms that you're adding. So it doesn't say to come out with a number. It says to come out with a formula in terms of one unknown, n, the number of terms that you're adding. Okay, let me do problem 14, because this will come out to a nice answer. Problem 14, 4 plus negative 4 plus 4 plus negative 4, etc. And so let's find the sum of the first n terms. So it's a1 r to the n minus 1 over r minus 1. Okay. And so S sub n is equal to, well, the first term is 4. The common ratio is negative 1. 4 times negative 1 is negative 4, times negative 1 is positive 4, times negative 1 is negative 4. And so this is equal to a negative 1 over r, negative 1 minus 1. So I get 4 to the negative 1 to the n minus 1 over negative 2. 4 divided by negative 2 is a negative 2. Negative 1 to the n minus 1. And so let me multiply the negative inside the parentheses. And so S sub n is equal to 2, 1 minus a negative 1 to the n. And so notice that your answer will either be 0 or 4. No. 4 times negative 1 is negative 4. Times negative 1 is a positive 4. So I keep multiplying by negative 1. So that is why the common ratio is negative 1. Okay? Let me do problem number. And so you notice here, when n is even, I guess I'm going to get 0. It'll be 1 minus 1. When it's odd, I'm going to get 1 plus 1. Oh, shoot. Turn that off. I just lost the connection. Turn it off. Off. Get off the internet. Oh, man. Connection. Hello. Come on. Let's go. Oh, come on. What are you doing? Shoot. Refresh. Oh, come on. Okay, good. See if I can do it. Okay, connect again. Come on. Come on. It says it's going. Okay. Good. Okay, come on.
Recording in progress.
Okay, good. I'm back now. Let's see. Can people hear me again? Hello? Can people hear me again? Okay. And let's see. Can you still see the writing in the background? The visual's gone. Okay. you should now be able to see it. Yeah, okay. Sorry about that. I lost the internet connection for a second. Okay, so um, so notice that when n is even, I have a negative 1 to even power is a positive 1. So 1 minus 1 is 0. So that means that if I add an even number of these, I'm going to get 0. Whereas if n is odd, then negative 1 to an odd power is negative 1. And so I get 1 minus the negative 1 is 1 plus 1. It's 2 times 2 is 4. So if I add an odd number of terms, just this first term, or maybe the first 3 terms, I get a sum of 4. But if I add an even number of terms, I always get 0. So the sum of an even number of terms is 0. The sum of an odd number of terms is 4. Okay. Let me do problem number 15. And so 3/4. Yeah, so what you notice here is that if you just add up the first odd number terms, you're going to get 4 always, because the plus and minus 4's cancel except for the last one. Whereas if you add up an even number of terms, the plus and minus 4's cancel, so you always get 0. And that's what our formula is telling us. Let me do problem number 15. 3/4 plus 3 over 16 plus 3 over 64. Okay. And so let's find the sum of that. Okay, so S sub n is equal to a sub 1, 1 minus r to the n over 1 minus r. And so let's find the sum of the first n terms. The first term is 3/4. The common ratio is 1/4 because 4 times 4 is 16 times 4 is 64. Therefore, 3/4 times 1/4 is 3 over 16 times 1/4, 3 over 64. So the common ratio is 1 over 4. That is correct. 3 over 16 divided by 3 over 4 is 1 over 4. And so 3/4 times 1 minus 1 over 4 to the n over 3/4. 1 minus 1/4 is 3/4. The 3/4 are going to cancel. And so you just get that the sum of the first n terms is 1 minus 1 over 4 to the n. And that is your answer. A very nice compact formula. Okay? Let me do problem number, let's say 17. It's 5.6. Okay. So first, what I notice is the following, is that I can add up so if you want to find, say if you want to find the sum of the first 5 terms of this sequence. So say you want to do 3/4 plus 3 over 16 plus 3 over 64 plus 3 over 128 plus the sum plus 3 over 256. And I say, well, what is that equal to? You just say, oh, well, I plug in 5 into this formula and I see that this is going to equal 4 to the 1 minus 1 over 4 to the 5th. So that's going to be equal to 1,023 divided by 1,024. And you go, oh, so that's an easy formula to do. What two terms? What terms are you referring to? Find the other two terms. Okay. Oh, no. So in other words, the formula, this formula adds up all those terms. You don't even have to calculate them. It it tells you if you find to find the sum of the first 50 terms, uh, you just plug 50 into that for that n, and it gives you your answer. You don't have to, calculate each term. N is whatever you want. It is the number of terms that you're adding. And so n is the number of terms that you are adding. Okay? Let me, well, it could, in the above case, I said add the first 5 terms, yes. But it could be, I say to add the first 30 terms, in which case n would be 30. It's the number of terms you're adding. Okay? If you're adding the first n terms. Okay, so let's look at an infinite series. So if you look up here, actually I even gave you like that one. So I look at here at this problem number 7. I said add up the first 15 terms. 1 plus 1/3 plus 1/9 plus 1 over 27, dot, dot, dot. Okay? And I got some number. Suppose I say, well, add up the first 100 terms. Well, what you'll notice is that the last few terms, they keep getting smaller and smaller and smaller. And so it could be that if they keep getting smaller and smaller and smaller, then they become relatively insignificant. And so it could be that if I add them all up, maybe, it comes out to some nice number. If you look here, the sum of the first 15 terms is 1.499. If you add up the first 100 terms, it's probably 1.4999. And so if you add up every term, maybe it approaches some nice number. So if r here is less than 1 in absolute value, then this guy here goes off to 0 as n goes infinity. And so you'll just get that if you want to add the first all terms, all infinite number of terms. Say I want to add up n equaling 1 to infinity of a1 r to the n minus 1. Well, it's going to equal a1 over 1 minus r, just like what we've seen above. Because the r to the n went off to 0. And this is so long as r is less than 1. But if r is bigger than 1, well, look at this. If you have, say, this case here. If you have this case here, 3 plus 6 plus 12 plus 24 plus a whole bunch of things that are becoming bigger and bigger, well, if you add up an infinite number of these, you're going to have a really large number. And so we say that in the other case, that this series diverges. It has some weird sort of value. It's what's called a divergent series. Yes. Oh, okay. So, meaning like, so if I look at, say, this 1 over 2 to the n, and look as n gets large. Well, notice that this is 1 over something very big. So what's 1 over a billion? Well, that's small. What's 1 over 100 billion? That's even smaller. And so 1 over something that's getting gigantic is getting smaller and smaller and smaller. And so it becomes something very tiny. Does infinity mean? Um, Divergent just means that it has, it's something called a divergent series. So uh, it's not convergent. So large is no, 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 no. The the reciprocal of something. Well, no, divergent could be. So I didn't want to get into the definition of a convergent and divergent. So a convergent series. So a convergent series a series is set to converge somewhat. So a divergent series is a series that does not converge. A series that's not a convergent series. A series is said to converge if, well, a series is said to diverge if it is not a convergent series. Okay? I don't want to say too much about that because that's all I can really say at this level. Okay. Um, so basically, what you're thinking is that, well, you know, let's matter of fact, let's look at this guy. Notice that as n goes to as n gets larger and larger, what is this sum approaching? Well, what's 1 over 4 to the n for n large? Well, as n keeps getting larger and larger, this total value is getting smaller because it's 1 over a very big number. And so if I add up 3/4 plus 3 over 16 plus 3 over 64 and add it up forever, notice that this value will approach 1. Okay? And so that's sort of a nice thing to know. Let's do problem number 16. Well, actually, let's do problem 17. Let me do problem 7. No, I see why. No, let's do problem 16. One plus 1/3 plus 1/9 plus 1 over 27 plus 1 over 81, etc. Yes, we're still in section 15.6. Okay, so in exercises 16 through 21, find uh, the sum of the infinite series if it exists. Okay, so let's do that. And so, well, the first thing to do is to figure out if the common ratio r is greater than 1 or less than 1. If it's greater than 1 in absolute value, then, I can't do this. And so the common ratio here is equal to, well, 1 times a third is 1/3. And so the common ratio is 1/3. Now notice that the common ratio is less than 1. Therefore, I can find the value of the infinite series. That says that the sum of this infinite series is just equal to a1 over 1 minus r. a1 is 1, r is 1/3. 1 minus 1/3 is 2/3. The reciprocal of 2/3 is 3/2. So if you keep adding all these infinite terms, then they add up to 3/2. Okay, so I'll show you how that happens in 1 second. How it won't exist. Why multiply and not divide to find the common ratio? Well, you can divide if you want. Doesn't really matter. 1/3, because I like multiplying, to me is easier than dividing. 1/3 divided by 1 is 1/3. And so notice that you always multiply by 1/3 to get to the next term. 1 times a third is 1/3 times a third is 1/9 times a third is 1/27 times a third is 1 over 81. So if you add up all these numbers, you get the exact value 1 1/2. What is 3/2? It's the sum of all these terms added up. Let's do problem number 17. 2 plus 1/2 plus 1/4 plus 1/8 plus 1 over 16. Okay, so now let's look at this. So notice that this is not a geometric series, but now I just put parentheses around this. This is a geometric series. And so the 1/2 plus 1/4 plus 1/8 plus 1 over 16, etc., is a geometric series. So I can find the sum. So first, let's find the common ratio of this geometric sequence, this geometric series, 1/2. No, the common ratio is 1/2. 1/2 times 1/2 is 1/4. Okay. Look. Okay, so this is not a geometric series. You cannot use the first term. You have to start at the second term and continue on from there. Starting from the second term and continuing on forever, that sum is a geometric series. So then let's find the common ratio for what is in the parentheses, the red parentheses here. Okay, and so that's the common ratio. The common ratio is 1/2. The common ratio is less than 1 in absolute value. So I have that the sum is equal to a1 over 1 minus r. But remember, that was for this in red. So I needed to add 2 to this, or I'm going to be in trouble. No. Okay, so first term of the geometric sequence. So the first term of your geometric sequence, the first term of the geometric series will be, a1. So in this case, look in the parentheses. Okay, so if you look in the parentheses, this is a geometric series. Okay, and so A1 in this case is 1/2. R in this case is 1/2. 1/2 divided by, well, 1 minus a half is again a half. 1/2 divided by 1/2 is 1. And so if I add up all these terms, I'm going to get the number 3. So 2 plus a half plus a fourth plus an eighth plus 1/16 plus add up, continuing forever, you get 3. So the sum of those terms, adding up forever, is 3. Okay. Let's do problem number 4. Well, that's easy. The easiest thing is, you see, that was an old paradox of the Greeks. I think it's Zeno's paradox, which is that you can never cross the street. Of course, they didn't say it in that terms, but let me make it into a more modern terms. And so Zeno's paradox says you can never cross the street because, well, if you try to go from one side of the street to the other side of the street, and we're going to do it the same way, we're going to do this. And so I'm going to do a half plus a fourth plus an eighth plus a 16th. Well, you can only go halfway across the street. Next, you can only go halfway across the, so you have halfway across the street left. So you can only go halfway there. So you have a fourth of the way. You've gone a fourth of the way. Now, again, you can only go half the way. You can go 1/8 of the way. So that's the sum. And so you never get there because you can only go half of what you did previously. And so you can never actually cross the street. But of course, that's ridiculous. Have you ever been able to walk anywhere? The answer is yes. The paradox was, well, in other words, they didn't believe in what's called infinity. And so if you don't believe in the term infinity, then that means that there is no motion in the universe. Everything is static. You do not move, nothing changes. Obviously, uh, we move. There is change. Okay? So, okay. So we do have infinity is the answer. Okay. You can accept. So I accept the fact that there is infinity. I accept the fact that we can actually cross the street. Okay. Let me do problem number 19. 1 plus 2 plus 4 plus 8 plus 16, etc. This is a geometric series. Notice the common ratio is 2, but because to go from 1 to 2, multiply by 2, times 2, 4, times 2, 8, times 2, 16. But that means that the common ratio here is greater than 1, and so the series diverges. Okay. What is the formula? Right there, it says if the common ratio is bigger than 1, then we say the series diverges. So that's what it is, diverges. Okay? Well, no, diverges. The formula is it diverges. And so the formula says it diverges. Okay? And that is a sufficient answer to the question. It's a divergent answer. Okay? Let me do problem number 'If the common ratio is greater than or equal to 1, then this infinite series diverges. If it's less than 1, then it converges and it's equal to a1 over 1 minus r. Okay, so let me do problem number 21. 3/5 plus 3 over 25 plus 3 over 125 plus. So let's find the sum of this infinite series. Because it's always easier because things get small and insignificant. Okay, and so notice that the common ratio, since I'm adding up infinite series, I want to see what formula I use. And so the common ratio is, well, 1/5, because I keep multiplying by 1/5 to go from one term to the next term. And so r in absolute value is less than 1. So that says that the sum of the first n terms is just a1 over 1 minus r. Oops. Of all these infinite number of terms is just a1 over 1 minus r. And so if I add up all these terms, I get a1, which is 3/5, over 1 minus the common ratio. Notice that 5 times 5 is 25, times 5 is 125. Therefore, 3/5 times 1/5 is 3 over 25, times 1/5 is 3 over 125. Therefore, the common ratio is 1/5. 3/5 times 3/20 is 3/5 times 3/25 is 9 over 125. Okay, so let's multiply and divide by 5. The 5's cancels, you get 3. 5 times 1 is 5. The 5's cancel. 5 minus 1 is 4. So if you add up all these numbers, 3/5 plus 3 over 25 plus 3 over 125, going on forever, you get 3/4. How'd you get 1/5? Okay. So 5 times 5 is 25. 25 times 5 is 125. Therefore, 3 over 5 times 1 over 5 is 3 over 25. Times 1 over 5 is 3 over 125. Therefore, the common ratio is 1 over 5. Okay, good. Can't see it. 5 times 5 is 25. 25 times 5 is 125. Therefore, 3 over 5 times 1 over 5. 3 times 1 is 3. 5 times 5 is 25. 3 over 25 times 1 over 5. 3 times 1 is 3. 25 times 5 is 125. Therefore, the common ratio is 1 over 5. If not, just divide. 3 over 25 divided by 1 over 5 is 3 over 25 divided by 3 over 5 is 1 over 5. Okay. Let me do problem number 22. Okay, so this is a so, this is a old story. A king who was who was very fond of chess. So this Arabic tale uh, is usually said a little bit differently. So it was saved by a person in a forest. Usually in a Arabic tale, it's the tale about the first person who made this game of chess. If so, the king was very happy and grateful and asked him for a wish. Sometimes this is said where uh, the person saves maybe a daughter, his daughter, um, for wish. This is page 6. Oh boy, now I lost it. This is, sorry, this is page 674. Okay, wait. Okay, wait 1 second. When I move this, I actually lose. Okay, okay, there you go. For a wish. This person said very humbly, "Oh, my master, if you want to grant me a wish, then please give me one grain of rice for the first square of the chessboard, 2 for the second, 4 for the third, 8 for the fourth, and so on. So they keep doubling. So each time you put something on the next square on the chess board, you double what was in the previous um, square on the checkboard. The king was amused, well, was amazed by this wish, and promptly granted. it is said that the king almost ran out of rice and found it impossible to fulfill the wish. Okay, so the question is explain why this is so. Um, there are 64 squares on a chessboard. And we'll assume that 100 grains of rice weighs 1 gram. Okay. Okay, um, so yes, so this is a old Arabic tale about uh, somehow you put 1 grain of rice on a chess square, then you double it for each subsequent square on the chessboard. So 1, then 2, then 4, then 8, then 16, then 32, etc. Okay. Um, when this was first told, I think, well, currently, I think usually when it's told, say, this is an old Persian tale, usually I think is done in terms of dates, but grains of rice are better just because it comes out to a nicer number. And so, actually, I think when I was told this, I was told it with pennies uh, when they told it to me in like 6th grade. Um, uh, Also, I've heard it where the person is in save someone in a forest, the daughter in a forest, and they give wheat. But rice is even better, just because it comes out nicer. Okay, so let's do this. So basically, what we want is, well, 1 grain of rice on the first square, then 2 grains, then 4 grains, then 8 grains, then 16, and you keep adding these all up, and you add up the first 64 terms because there's 64 squares. Yeah, but it turns out to be a lot. Well, we'll actually see how much. hmm Since there are a chessboard is an 8 by 8, and so there are 8 squares by 8 squares, so a total of 64 squares. So let's do. Well, I know that the sum of the first n terms is just r to the n minus 1 over r minus 1. Yes. Okay. And so let's add these up. So let's add up the first 64 terms. Well, the first term is 1, and we get 2 to the power 64 minus 1 over 2 minus 1. And so 2 minus 1 is just 1. And so we get 2 to the 64 minus 1. Okay, so that's a large number. So this is approximately, no, this isn't, this is an old, this is an old Arabic tale. Uh, this is, it was in literature. It's not, this is not from a mathematician or anything. This is in literature. It's actually one of these Persian tales. Okay. Yeah. Well, it is based on fact. It's based on the invention of the game of chess. So this is actually, so when it's normally told in Arabic countries, it's actually about the inventor of chess, that he wanted this. So it's some sort of tale about this. So 2 to the 64, it's approximately 070 grains of rice, approximately. Okay. And so it's going to be much more than that, by the way. Um, it would be thousand, million, billion, trillion, quadrillion. It would be 184 quadrillion dollars, by the way, if you do pennies. Okay, so that's why it becomes unreasonable when you do pennies, because that's just too much money. Okay, so this grains of rice is a little bit better because it's at least smaller. Okay, so we have 100 grains, and so this is approximately 184 467 440 700 000 um, grains, grams of rice. Wait. I'm sorry. Sorry. Uh, so let's see. Grams of rice. Okay, so let's. Sorry, I'm looking here. That's one, two, three. One, two. Yes. Yes, you would need scientific notation for this. That's why it's an approximate, because I can't go all the way out. My calculator doesn't go out that far. Okay, so that's how many grams of rice. So let's do kilograms. So this is 184 467 440 700 kilograms, because there's 1,000 grams in a kilogram. So that's kilograms of rice. Let's do metric tons. And so that would be approximately 184 467 440 700 metric tons of rice. So usually things are done in metric tons when you are transporting rice, like in a across the seas in a gigantic ship. So 1,000 million billion. So 184 billion metric tons of rice. So that is literally more rice than they have in China. So that's a lot. Metric tons. hmm So there are many differing ways of saying tons. I'm saying a metric ton. Okay. And so approximately 184 billion metric tons. Okay, so let's talk about money annuities. Yes, so it's a 2, 4, 6, yeah, something of that sort. 17, 2, 4, 6, 8, 10, 12, 14, 16, 19. So it's 1.844 times 10 to the 19 grains, 10 to the 17 grams of rice. Okay, so let me talk about an annuity. So an annuity is a financial instrument where you put either you input the same amount of money into this instrument uh, at the same intervals of time. And so maybe you're putting in $100 every month or whatever, or you're taking out the same amount of money every unit of time. And so maybe you have a mortgage and you're paying off $2,000 every month. Okay. And so that's an annuity. And so and let's use this notation. Let R be the interest per period. So let's not do this per annum. Let's do this for some period of time. And let N be the number of periods. And let P be the principal, be the amount. Well, and say let's put money into the annuity, amount input into the annuity per period. Okay. When you're paying it off, that's the amount that you have to pay off per unit per period. So that says that this month or whatever this you put in P dollars. Last month you put in P dollars, but you got some interest, some fixed interest. So let's say that this is a fixed interest annuity. So this is a fixed annuity. So I'm talking about a fixed annuity here. And so the next month, the previous month, you put in P dollars. You got your 2 months of interest. And do that for that's right. This is just telling you how much money you currently have in this instrument, where you have input P dollars per period, having a fixed interest of R per period. And let's do this for N periods. Well, if you do that, well, by the formula, recall that S sub n is equal to A1. Oh, I see. You'll get confused with this R. R to the n minus 1 over R minus 1. Okay, so the amount A is equal to the first term, P, R, but R in this case is this guy that I'm multiplying by. 1 plus R all over, 1 plus R minus 1. The common ratio. So the common ratio in this case, So R, maybe I should call this R in this case is the common ratio. I'll capitalize it. So unfortunately, this R here is the interest rate. So when you're talking about interest, was a goal. Okay, so I've been figuring. Let me write the formula down. So let me cancel out the ones, and so A equals P 1 plus R to the N minus 1 over R. So this says that this is the amount of money you have in a particular fixed annuity. So this is a fixed annuity. This is the amount of money you have in a fixed annuity given that you put P per period for a number of n periods at an interest rate of R per period. Okay, and so this tells you the amount of money you have. So let's do an example. Okay, so let's do an example here. Suppose you invest, let's say, maybe, let's say $100 per month. And let's say that you invest this into a IRA, let's say a Roth IRA. So invest $100 per month into a Roth IRA. In a Roth IRA, your any, anything that you make, at least if you hold it into an account for 5 years, anything that you make will be tax free, and so all your interest is tax free. And so let's say that you do this for 20 years at 12% per year, compounded monthly. Okay. How much money? Yes. Okay. So, um, you then keep it in this account. In this IRA, but you do not add, you know, either add or subtract money. You do not touch this money. Um, let's say for 50 years. How much? Tax-free money. Do you have? at retirement. Okay, so $100 per month is not unreasonable amount. And so let's say that, so the amount A is equal to P, 1 plus R to the N minus 1 over R. Okay, so let's plug this in. So you put in $100 per month, and every month you get 1%. So 12% divided by 12 is 1%. And so it's 1.0. And you do this for 20 years. 20 times 12 is 240 over 0.01. Okay. And so let me do that. And so if I plug that into my calculator, I get, oh, and so that's how much money you have. So A is equal to 10000, 1.01 to the 240 minus 1. That's the amount of money you have after 20 years. Now let's see how much money you have. Right. So now let's see how much money you have at the end of when you start to retire. Okay. And so recall that I'll use the simple interest formula. So let's do that. I start out with 10,000, 1.01 to the 240 minus 1, and I do this for 12 times 50 years. So 12 months a year for 50 years is 600. So maybe I'll just write this as 1.01 to the 600. And so this is, well, let's see, 100, I'm sorry, so 4 zeros times 1.01 to the power 240 minus 1, 1.01 to the power 600 is 38737.65 approximately. $38 million. Sorry. Oh, I can just plug it into my calculator. So I just plug that into my calculator. I have an exponent button. So I just plug in 1.01 to the power 600. Plug in 1.01 to the 240 and multiply, and well, subtract 1 and just multiply those numbers together. And so you put in $100 per month, probably what you pay for your cell phone. At retirement, you have 39, almost 39 million tax free. Okay. What do you mean, how much a month? Uh, so this is, after at retirement. So this is at retirement. He doesn't put any money in after what is monthly saving amount. He didn't put zero. He plugged in. He put in zero. Remember, uh, after the initial amount, he didn't put in. He put in $100. That's it. So, oh, are you saying how much total? Ah, okay. So actually, let's see this. So note, he put in $100. The total amount from his pocket that was invested is, well, let's see. So the total amount that he invested was $100 per month, and he did this for 240 months. So that's $24,000. So notice that he invested $100 per month. So that is a little bit over, well, $1,200. And so he invested $1,200 per year for 20 years, a total of $24,000. He stopped, after he did that $24,000, he just said, well, forget this. I'll see how much I have at retirement. He has around $39 million at retirement. Yes. What do you mean? You invested early. What do you mean? How do you do that? You invested early is the answer. It's the same way that how are people so much in debt? Is because they take a long time to pay it off, and so it works in reverse. Either if you invest early, then you have tons of money at the end. If you go into debt early, you're in debt and there's no way to get out of it. Yes, not 24,000 grand. It is $24,000. Gives you yeah. hmm Okay. So let's solve this for P. This is no okay. So I have yet to finish off. This is still section 15.6. There's still section 15.7. Okay. So let me give you the present value of an annuity. So the present value of an ordinary annuity. How much do you have to input so that after a fixed amount of time, inputting into, yes, that is correct. Section 15.7 is tomorrow. And so how much do you have to invest so that, okay, so how much do you invest into a annuity so that at the end you have some amount that you want? And so that's called the present. So what's the value of the amount that you're inputting? And so the present value of an ordinary annuity is just A0 equals P 1 minus 1 plus R to the negative N over R. Okay, so let's do an example. Let's say problem number 30. Suppose that you win a 37 million, oh, $440,000 lottery. This will also, uh, you'll be able from this to figure out how much when they give you, say, if you win a lottery, how they figure out what you get per month and how they figure out, well, if you want to get it in just a lump sum. And that lump sum is really the present value. Right? And so this is still, we're talking about, this is still looking at a geometric series. So problem 30, lottery. You decide against taking a lump sum payment, payout option of 16,800,000, and instead, and will instead receive $120,000 per month for 26 years. So this is the usual sort of amount that they have for state lotteries. Some are different, but usually it's per month for 26 years. That's sort of semi-standard. What single deposit So now we're going to look at this from the standpoint of the state. And so, what single deposit should the Lottery Commission make now to fund your lottery winnings? And so it's going to be no, it's obviously it's this formula here. It's the present. I'm asking you for the present value of an ordinary annuity, right? That's why I'm asking you. So it's that formula. So assume the commission is able, usually for states and all that, they actually have a fixed annuity that they're actually guaranteed because they're a very big entity, and it's actually not too bad. So this is actually, I think, what the state of California gets. So assume the commission is able to invest. I think I actually looked this up for what the California Lottery Commission gets. invest in an account that pays 7.2% annual interest compounded monthly. Okay. So it's 120. So it's done for 26 years. Yes. So you do it. If you multiply that out, that should give you the total amount of your winnings. Okay. So if you do that, it's 12 times 26, which is 312 times 120,000, gives you your 37,440,000. Okay, so if you just multiply that out, that does give you your total winnings after 26 years. Okay, so now the question is, well, um, how much if the California uh, Lottery Commission wanted to fund this, how much money do they have to put in to this investment, to this fixed annuity that pays 7.2% interest compounded monthly, so that they can always take out $120,000 per month, and they'll have money uh, for the next 26 years. After 26 years, they'll be out of money, but in this account. But they want to be able to take out $120,000 per month for 26 years. This is also, when you retire, how you figure out how much money you can take out, right? This Okay, so you don't run out of money uh, during retirement. Okay, so A0 equals P 1 minus 1 plus R to the negative N over R. So let's use this formula for the future value, for the present value, sorry, of an ordinary annuity. And so R here, well, P is what, $120,000. R is 7.2% per month. And so 0.006% per month. N is 26 years. And so let's multiply by 12 to get the number of months. And so 312 months. And so let's plug this in. So I should invest $120,000 at 1.006 for 312 months over 0.006. Okay, and that's the amount. But now let's find the approximate amount. That is correct, because you move your decimal place 2 places over. So 7.2% is 0.072. Okay, so let's plug into your calculator. So you get approximately 16,906,429.547302, which is approximately 16,906,429.55 cents. So you should put in almost $17 million into this account. You're then able to take out $120,000 every month, and you'll have it, uh, and you won't, you'll still have money uh, for the next 26 years. Okay, and so that's the amount of money they need to put in so that they can fund this. So if you actually look at this, uh, the payout, the lump sum amount is usually very close to this amount. So if you actually calculate this, this was actually done. I actually did it for a particular winning for California lottery, and it came out to be almost exactly what the lump sum was payout. Yeah, it's very close. It's actually very close. Okay. Um, they, yeah. So right. So actually, I think they said 16,800,000. Well, they get okay. So they get an extra $100,000, but it's pretty darn close, right? I would do I would take the amount of money over 26 years. Okay, so uh, okay, let's do mortgages and loans. Um, this is the amortization formula for equal payments. Okay, so if you yeah, it's a safer bet. Yeah, paid 674. Okay, not only that is well, yeah, so uh, you can also make investments with that also. Okay, so um, if you purchase something, let's say you're purchasing a car, uh, usually what happens is uh, the bank uh, purchases this, the car. You then get a loan for a certain amount, and you pay back this loan at some uh, equal amount per, say, month. So maybe you pay, $500 every month for this car, or maybe you were purchasing a house, and you pay $2,000 every month for the house. And so the question is, well, how do they figure out how much you should pay every month? And so let's use the amortization formula. And so it's basically you just solve this equation here for P. And so if you solve that equation for P, you get that P is equal to A0R over 1 minus 1 plus R to negative N. Okay? So, let me do an example. This is so for most um, loans that you get, you have a fixed amount that you pay every month. Okay? So this is the formula for figuring out how much you must pay every month. Now, of course, if you pay early or whatever, you'll have to recalculate what you have to well, you would still, it depends on the entity that's loaning you the amount. So let's just, there are many different rules depending on if you want to pay off a loan early. Sometimes they actually have you pay penalties if you pay early, whereas other ones you don't have penalties if you pay off early. So let's have it as a fixed amount. What is A? Oh, same as before. These are all the same. So uh, R is the interest. Here it is. It's way up here. There it is. R is the interest per period. N is the number of periods. Okay. And A0 in this case is the amount of loan. And so, and P is the payment. So instead of here, instead of uh, instead of calling it the amount that you input, it's the amount that you pay per, pay for the loan per period. So P is the amount that you pay per period for the loan. Yes, that's what I'm doing right now. So, so let me write my example. Okay, so let me do the example. Okay, so example. Okay, suppose you take out, you take a 30-year okay. So suppose, yes, this is the last one. You take a 30-year mortgage, 30-year mortgage of, let's say, $700,000. So you have a $700,000 mortgage for your new house. Let's say it's a house, not a car. And I will be telling you that at 4.8% annual interest, compounded monthly. Okay. Determine your monthly payments on this mortgage. Okay, so let's do that. So I have, yep, okay. The amount you will pay per month is A0R over 1 minus 1 plus R to the negative N. Okay, so you take out a $700,000 loan. You have an interest rate of 4.8%. And this is per month. So you're going to have to divide by 12. So 0.048 divided by 12 is 0.004. Yes. Oh, no, 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 no. No. And so 4.8% is 0.048. divide that by 12, so you get 0.004. And 30 years, there are 12 months per year, so 360 months. Okay, so I did all these formulas rather than doing it per annum. I did it per period, so the formulas look easier. A lot of times, well, if you did this in a finance class or whatever, they'd probably give you the formulas per annum, and they'll be really complicated looking. So, okay, so this is equal to P is equal to A0, 700,000, R, 0.004, over 1 minus R, 1 plus R, 1.004, the negative N, 360. Okay, so this is approximately 2134.69406,475, and so this is approximately $2,134.69. So that's the approximate amount that you would pay for the mortgage. Yes, those are more complicated. Okay, so each of those are a little bit more complicated. You need more math to discuss those. Okay, so let's do problem number. Oh, I did 4.8 rather than 3.6. I see that was 32. How about, yes. How about problem number 34? Suppose you take out a 5-year loan of $45,000 for your new car at 4.8% annual interest. Compounded monthly. Determine your monthly payments on this car loan. Okay, so let's do that. So P equal A0R for 1 minus 1 plus R to negative N. So A0 is 45,000. R is 4.8% divided by 12. 0.048 divided by 12. 0.04. 0.004. N is 5 years. So there are 12 months per year. So you have 60 payments. So let's see how much you should pay. Oh, I should actually see how much you actually pay. Actually, it won't be too much, but okay. Actually, I should have done that on this. How much do you actually pay for the house? I'll do that also. Okay, so um, I'll do that one instead. So let's see. This is equal to P is equal to A0 R over 1 minus 1 plus R to the negative N. I'm just plugging it into the formula. And so P is approximately, let's figure out what that is. So 45,000 times 0.004 divided by 1 minus 0.004 to the power negative 60 is 845.0883905. And so you pay $845.09 per month for your 5-year loan. Yeah, well, so now, well, let's actually, so this one last, so one more minute from the previous example. How much do you pay the bank for this $700,000 home? Okay. Yeah. So let's look here. So you paid uh, this amount here for 360. So the total amount that you pay would be the how much you pay per month times the number of months. And so this was equal to, of course, I'll just give the approximate amount. I'm a cheat. It's this amount. Okay. Times your 360. So it was this amount times 360. And so let's plug that in and see how much it is. Yeah, 360 times the 2134. Let's see how much you actually pay. So 700,000 times 0.004 times 360 divided by 1 minus 1.004 to the power negative 360 is and this is for a very low interest rate, 22156.693. And so approximately 1,322,156.69. So you pay about $1.5 million. Yeah. No. You can also do that. You just do 360 times the 2134. They'll give you something approximate. The Actually, let's see. Times the I wonder why I got something different there. Okay, so that's how much you uh, will be paying off. So it's your $700,000 home is really uh, you know about half of it, or well, you're paying about double that amount. Okay, so that's it for today, and I guess I will see you tomorrow at the same time. A lot of the techniques are not different. Uh, so there are many fewer techniques than what you're counting. Right. So a lot of them come down to really the same. You're just sort of doing the same thing more than once. Okay. Um, for this, there'll be several. Yeah. So I would say the best thing to do is to look at the sample exam and go over the sample exam uh, and be sure that you can do it because the actual exam is nearly identical to the sample exam. Okay. I will be giving you formulas on the final, um, and I'll try to remember to put the formula sheet up online on Educasoft so you can see it. Okay. So that's it for today.